and I think we're going. Okay. All right. Did anyone, before we move forward with the next part, did anyone have any questions about functions and closures for anything that I didn't, cover, or something that you're wondering about? Dope. Okay. So, data structures in Swift. I need to move the mouse so it's not hovering in the middle, because that would be aggravating. Excuse me, mouse. Let me just look at my target here. Okay. So, but I do need to click on it so that I'm in focus. Then move the mouse off. It's a whole process here, guys. Bear with. Okay. Cool, this is working. All right. Strings. So the first of the data structures that we're going to be looking at in Swift are strings. I hear you asking a question in your mind. Why are we talking about strings as a data structure instead of as a primitive type? Well, that's because strings are kind of like a primitive type, but they're also kind of like a data structure. In a way, a string is an array of character objects or character types, right? So that's why we're talking about strings. So we've seen a lot of this stuff in examples already, so I'm not going to equivocate too much on it. And I would assume that in whatever language you all know, because I know a lot of you know JavaScript, Python, Java, that sort of thing, most of these things I'm going to talk about in this lecture exist in those languages in one form or another. I'm mostly going to be teaching about the syntax rather than the theory behind them. Although I will teach a little bit about the theory as a quick refresher for anyone who doesn't remember exactly how you access a value from a dictionary. But to start with, we're going to look at string literals. So, a string literal is wrapped in quotes. It is a collection of characters. It has a number of helper functions provided by Swift. That's actually just strings, not string literals. Apologies, it's a poorly named slide. This is a string literal. It has quotes around it, and it gets a special color. That's how you know it's a string. It's orange. Strings are the only orange thing in Xcode, okay? I don't know if that's true, don't quote me. Strings have something called interpolation. In a lot of other languages, the way that you do this is by, having the first part of your string literal, where you're like, oh, this is a string, and then that's one string literal, and then you close it out with the end quote. Then you put a plus, then you put the variable that you want to show up, and then you do another plus, and then you put a new string literal afterwards. And that's how you kind of compose together the string where you want to put a variable into the string, right? In Swift, you use what's called interpolation instead, where you use this special syntax, which is backspace, open parentheses, your variable or expression, close parentheses, okay? So within there, you can place a variable, you can place a constant, or you can place an expression that evaluates to a value. In this case, we are using the variable named 10, which has the value 10 inside of it, which is an int, and we are using this interpolation to say, hey, place 10 inside my string. This is one of the few places where Swift has something that looks like type coercion, but it's not type coercion. There's a lot of weird stuff happening here, but basically, if you'll recall, when we looked at the print definition, it started with a variadic parameter that could take in any type. What this is doing, syntactically, it's hiding the fact that we're passing this 3 parameters. We're passing it the first part of the string as one string. We're passing it the 10 variable as a int, and then we're passing the second part of the string as a string. And then the print function does all sorts of magic stuff where it says, oh, okay, if it's an int, then this is how we turn that into a string, right? But it does it in a type-safe way. But you wouldn't know it. because Swift is it cares a lot about making your code easy for you to write and easy for you to read. So rather than being strict about types and also forcing you to be very, very verbose, it tries to be strict about types and then give you shortcuts while staying strict about type. Okay. String concatenation. So basically, if you want to add to a string, you can use plus equals, which is the addition assignment operator. You're probably familiar with this from other languages, but this is essentially the same thing as saying composition equals composition plus the string literal and it's okay, right? Or and that is okay. So that can be condensed to plus equals. Interestingly enough, one of the things that Swift does not have is the plus plus or minus minus operator. In Swift, this is more for ints and doubles, and I'm on a tangent here, so, humor me. But when you do plus plus, the idea is that it just increases your value by 1, or minus minus, it decreases it by 1. And then in something like C++, you can do the minus minus in the front or the plus plus in the front, and that changes the order of when it happens when you're using that in a for loop. It's nonsense. So in Swift, they dropped that, and they say, look, if you want to increase by 1, just be explicit. Use plus equals 1. Does the same thing. It's like 3 characters more. It's easier to read. Anyway, but that's got nothing to do with strings or string concatenation, so yeah. So for strings, pretty much, the most important stuff is knowing literals, knowing how to use interpolation in order to place variables into strings or constants into strings and print them, and how to combine strings together. There are also a number of other things that strings do, a lot of other things that you can do with strings, like finding substrings and breaking them apart into other strings, and all of that will be in your reading for this class. So make sure to read that and try to learn and understand it. However, there's a lot that we have to get through, so we're moving on to collections. I leave the reading to you. So collections consist of a number of things, including arrays. Arrays are a collection. So what are arrays in theory? Arrays are an ordered list of elements, okay? This is a grouping of elements where order matters. In an array, every single element must be the same type. This is once again Swift being very, very specific and very finicky about your type. Arrays can be nested so that you have multi-dimensional arrays. So you can have arrays within your arrays, and that gives you a matrix. And then if you do another array within another array, then you have a 3-dimensional matrix. And you can even create 4-dimensional and 5-dimensional ones and perform all sorts of crazy linear algebra matrix math if you want. I will not be asking you to do that, don't worry. In arrays, you tend to access the elements of the array by index. That means the number in the list. Because they are ordered, this is something that you can do where you're just like, oh, I just want something at index 2, right? They are the things that we tend to use arrays for are iterating if we need to go through the entire group of elements. Then array is an excellent use for it, especially given how it packs the memory. But that's like one of those optimization things that only matters if you're building a server that's getting 1 million TPS or something like that, right? Which you tend not to do with Swift anyway. Server-side Swift exists. I will teach a little bit of it later in the class. However, it tends not to get used in industry terribly much, even though it's super fun and cool. The other thing it is good for is if you know the index of the element you want, you get instantaneous access. So you don't have to search for it, you can just grab it. But that's only if you know the index. Okay, so let's look at arrays. So to instantiate arrays, we define the array type, which is array, And this thing, which is like a less than sign and a greater than sign and type within, that's what's called a generic. We will be learning about generics in class 3 or 4, one of those two. One of the next two classes you'll learn about generics. For now, all you need to know is that this is saying, hey, this array holds ints in it, okay? So yes, then we have over here what's called an array literal. So much like a string literal, much like a int literal or a double literal or a Boolean literal, arrays can also have literals that have within them literals of the type that you're using, or variables that hold the type that you're using, right? The way you define an array literal is you open it with a bracket, a square bracket, not a squiggly bracket. I realize I've been calling squiggly brackets brackets, and I'm going to continue to do that because they are referred to more frequently than square brackets, even though these are technically brackets and those are technically squiggly brackets. But these are square brackets. That is the case moving forward for this class. So square bracket, you open up, then you do a list of your elements that you want to instantiate with, that you want your array to have within them. In this case, we do 10, 3, and 5, and 6. You put a comma in between them, much like you do parameters for calling a function, and then you close it with a square bracket close. Swift also has a fun thing to make your code a little bit more readable, where instead of doing the array generic wrapper thing around int, you can just use square brackets to say, hey, this is an array type. This is one of those little things that Swift does to try and make your life easier. It's called syntactic sugar. It tastes good, and it looks nice. Of course, because Swift is very good at inferring type from literals, you don't need either of those. If you just pass it a type, or pass it a array literal that has elements that are all the same type, it is able to infer, oh, it's an array of ints. Now, if one of those was a double, you'd get a compiler error, of course, because it's very strict about type. When you want to access an array, you also use square brackets. You'll notice with arrays there is a theme here. It's also true for all collections. We tend to use square brackets to access elements in a collection. So here we use the index of the element. So we refer to the array identifier for our constant, myArray. We open right afterwards with a bracket. We pass in the index, which is always an int, which in this case we pass in the index 1. And arrays are 0 indexed, meaning the very first index in an array is 0. That is the cause of many off by 1 errors, and it will be throughout your entire career. I've been doing this 15 years. I get off by 1 errors all the time. Maybe that says something about me, but I think from what I remember, I'm pretty sure everyone runs into this and then is like, oh, right, off by 1, after spending 3 hours trying to debug it. So don't worry too much if you get an off by 1 error. You're in good company. So here we access index 1, which is the second element in the array. So we print the value 3, because that is what the second element is, the element at index 1 in the array. You can also iterate through an array using a for in loop, as we've seen in the previous class when we did for loops. We used ranges back then because we hadn't learned arrays yet, but a range is essentially a shortcut for creating an int array between two values. At the end of the day, that's kind of what a range evaluates to. It's not exactly true, but you can think of it that way. Whoop, and I hit a wrong button. So give me 1 sec. I'll pull this back up. Boop. 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 Yeah, I don't know why this thing has like a button that's like, yeah, just close the whole slide deck. I'm like, why would I want that on my clicker? So here then we enter the for loop. we hit the print function. In this function, we are using the optional parameter terminator, the one that has a default value of /n, which is a new line. Most of the time when you print using the print function, it prints it and then ends with a new line. So what goes to the console is whatever your string that you passed in was, and then it moves to the next line for the next thing that you print. If you pass in a terminator of empty string, which is what we have here, then instead of having a /n appended to the very end of your string, it doesn't, which means that this prints 1, 0, 3, 5, 6. All in a row, no spaces, no new lines. All right. So, sets in theory. That was strings. Not strings, sorry, arrays. So, sets in theory. Okay. So a set is another type of collection, much like arrays. However, this one is unordered. So arrays are an ordered list of elements. A set is an unordered grouping of distinct elements, and distinct is really important here. If you're familiar with sets and set theory in mathematics, that is not surprising to you, but it's good to call out if you're not familiar. So every single element in a set is the same type, just like in an array. It can be nested to create multidimensional sets, just like an array. The elements of a set must be what's called hashable. This is how sets operate kind of under the hood. They take whatever element you try and place into the set, and they generate a hash, which is intended to be a mathematically unique identifier for that value that is basically used as a key that you can then access it with later. But for now, you just need to know that most types defined by Swift, things like int, double, string, all those, are hashable. So you don't have to worry about it. If you're creating your own custom type, which we will cover in class 3, and you want it to be used in a set or as the key in a dictionary, as we'll see, it needs to be hashable. So you'll need to make sure that you either implement that or set it up in such a way that it can hash automatically. When you are accessing a value in a set, you tend to do it by the value itself, which bears the question, why are we accessing it? Sets are interesting because they are essentially a way of saying, yes, something exists. Yes, this is here, in fact. For the most part, when you're using a set, you're not really accessing its values to say, hey, I'd like to get this out of storage, like you do with an array. Right? An array is a way of storing stuff, and you pull it out. With a set, it's more like you're saying, yeah, I want to say that this thing exists, I'll add it to this set, right? And then you check to see if the set contains that element. So it is best used to look up if something exists that you have previously set. To check to see if you've added something to the set. This is also why distinct is important. So if you ever add an element to a set that is already in the set, it just ignores it. There's no duplicate entries in a set. There's only ever one of that entry, and it uses the fact that elements must be hashable to guarantee this. Okay, so let's look at instantiating a set. Once again, we have something like a type, right? Where we say, hey, we've got this set less than, string, greater than. Once again, this is generic. This is a generic, you don't have to worry too much about it, but what we're saying here is that the elements of this set are strings. You can also, of course, just say, hey, I want this to be a set, and Swift will know, even if you're passing it what is on the right-hand side, an array literal, it recognizes, oh, if you're passing an array literal that has as its elements strings, then this set variable that you're creating has string set for all of the elements within the set. String set for the elements in the set. My goodness, that is a hard sentence to parse. Right. So we use an array literal of strings. We pass it into the set variable, and the compiler makes sure that that variable, or constant in this case, has as its type a set of strings. So one of the things that you can do with a set is you can get a count. You can also use contains. You can use insert. There's a number of methods or functions on sets that you can use. For now, we're going to use two. We're going to use count, so fruits.count. And what this does is it prints the value 2. It tells us how many elements are within the set. Why is it printing 2 when we passed in 3 elements? Because they are not distinct, what we passed in. Banana and banana are the same, which means it dropped the second one. When it tried to be added to the set, it dropped it, because it doesn't care. It only cares if it exists in one way in the set. Likewise, we can call fruits.contains, pass in an element, in this case a string literal, and get back a Boolean, true or false. Is it in the set? In this case, melon is in fact in the set, and so melon found gets printed after 2. So that's sets. They tend not to get used that much, so don't worry about them too much. I wish there was a clock in here. Actually, wait, if I flip this around, do I have a clock here? Woo! Yep, there we go. Did it again. Apologies, everyone. Boop. 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 And boop. I just realized I should make sure that the QuickTime player is still recording. I think it is. Okay, cool. And then I was trying to find a clock, but yeah, I can't pull one up. All right, don't worry about it. I ruined it for nothing. All right, dictionaries in theory. So a dictionary is an unordered grouping of key value pairs, okay? So much like a set, it is unordered, so it is not, you can't sort it. You can't rely on its order. You can't access elements by index. If you were to iterate through the elements and go and say, oh, just give me all of the elements, I just want to see them all, and just go through that, it is not guaranteed to be in the same order every time you do it. That has to do with how it gets stored on memory and all that stuff. You don't have to worry too much about it. Just know that it's unordered. In a dictionary, because the elements are key value pairs, all of the keys must be the same type as one another, and all of the values must be the same type as one another, okay? Keys do not have to be the same type as the value. They just have to be the same type as each other, as all the other keys, okay? You could think of it as 2 arrays, maybe, although it's really more like a set for the keys and an array for the values, but whatever. You can nest dictionaries, so the value for a dictionary can, in fact, be a dictionary, which means you can get kind of these multi-dimensional dictionaries, just like with sets, just like with arrays. Keys must be hashable in dictionaries, just like elements needed to be hashable in sets. So keys need to have distinct hashes, and the grouping of keys in a dictionary is essentially a set. You can only ever have one of each key in a dictionary, okay? So if you add the key banana to a dictionary and you set that to, a value of, 10 or something, right? If you then try to add the key banana to the dictionary with the value of 5, it's just going to overwrite your pre-existing key value pair. And we'll look a little bit at that after the theory slide. When you are trying to access values in the dictionary, you use your keys. So basically, in order to get access to that value 10, you would use the key banana. And then dictionaries in Swift have this really cool thing where a key-value pair can be decomposed into a tuple. This is more syntactic sugar, but basically it lets you very, very quickly and easily, when you're iterating through a dictionary, have access to both of the key and the value for each key-value pair in the dictionary as you iterate through it. Dictionaries are best used for searching for something as long as you know the key. In programming interviews, dictionaries, also known as maps, also known as hash tables or lookup tables, I think. Yeah, I think so. Are often used in getting your best runtime for an algorithm that you are creating during a programming interview. Not always, but often dictionary is how you improve your runtime complexity. We're not going to talk about runtime complexity in this class, but if you ever want to talk about runtime complexity, feel free to come during my office hours and I will explain it to you. Big O notation is neat. I think it's cool, and I wish I could go over it, but we don't have enough time. So, instantiating a dictionary. Once again, we can look at the big exploded version of this. I'm guessing that you have a sneaking suspicion there is a cleaner, easier way to do this in Swift. You are correct. This is bulky. It's hard to read. It's very cumbersome. It's a lot of boilerplate. These are all things people say when they're talking about clunky languages like Java. This is how you do it in Java too. Very similar, right? I think it's not dictionaries in Java. I think it's dictionaries in C# and it's hash tables in Java, but I don't remember. I haven't used Java in years, so. But you have to use the generic notation. You're saying, hey, my keys are strings, my elements are, or my values are ints, right? And therefore, it knows that the elements are key value pair of string to int, okay? So this is the big gross way to do it, the technically correct way to do it. Swift has a much nicer way to do it, of course, which is with the brackets, square brackets. So when you create a dictionary type, much like you do for an array, you put a open bracket and then some type information and then a close bracket. But the key difference for dictionaries is that you have a colon in here. The colon says, hey, whatever's to the left of me is the key, and whatever's to the right of me is the value in the dictionary. Okay, these are the types. So I'm a dictionary that has a type of string for my keys and int for my values. Oh, I just realized. So the other thing is that this, on the right-hand side of our assignment operator here, we have a dictionary literal. This is an empty dictionary literal. Much like an array literal, which is an open square bracket, closed square bracket with a bunch of the elements in between. I didn't show it, but you can also have an empty array literal where you just don't have any elements. Just a open square bracket, closed square bracket. Same thing here, but you do include the colon to make sure that it knows, hey, this is a dictionary literal that's empty instead of an array literal that's empty. So, in Swift, you can do this to add to your dictionary. Some languages require you to call .insert in order to add stuff. I'm pretty sure you can do it like this in Swift. I was doing it in the playground in order to copy and paste it into this, and I wasn't getting errors, but now I'm second guessing myself, so maybe we'll play around with it after the slide deck is done, just to make sure. But at minimum, if it already exists, if the key giants already exists within the dictionary, you can assign a value to it, and that will override whatever value is assigned to the giant's key at that time. And then I'm pretty sure Swift has just a nice little helper thing in here that says, hey, by the way, if giants doesn't exist, make it, right? If the giant's key isn't here and doesn't have a value, just make it. So this is a way to, after you instantiate your empty dictionary, to just add a bunch of stuff to it, right? However, you can also, when defining your dictionary literal, just do it there. And so now you have your dictionary, and it's got all that stuff in it. So you've got your keys, giants, and your value, 14. Key, jets, value, 7. Once again, you use a colon, right? So you have your key, which is a literal, a variable, a constant, or an expression that evaluates to a value, right? So that's what you have to the left-hand side. You have your colon, and then you have your value, okay? And the types need to line up with your key type and your value type. Cool. So when you're accessing a value in a dictionary, the way you do it is by using the key. Just like when you're assigning to a value in a dictionary, you do it using the key, or when you're assigning to a key in a dictionary, you use a value. When you access a value, you use a key. Basically, the key is kind of the way that you say to the dictionary, hey, I would like whatever you have stored in the value for this key, whichever value is associated with this key, okay? So in this case, we are accessing the key, or we are inputting the key giants to access the value 14, because giants is associated with 14. If we wanted to pull out the value 21, we would pass in the key Seahawks, and so on. So this is that decomposition to a tuple thing I was talking about before. Basically, when you are iterating through a dictionary, which you would not expect to do that often, given that dictionaries are more for doing lookups, but you will often find in practice you do a lot for some reason. You will find yourself iterating through a dictionary frequently. The way that this gets done in a lot of languages is that the dictionary has a property you can call called like .keys, right? So you can do like my dictionary ID .keys, and that returns a set of keys, and then you can iterate through the keys, and then while you're in the for loop, you can then pull the value out by using that key, and because it's constant time, it's not impacting your runtime complexity. However, it's cumbersome and kind of a pain to do. So Swift decided to say, hey, you know what? A key value pair is basically a tuple. It's not exactly a tuple, but it's basically a tuple. So if you want to just, when you're pulling a key value pair from a dictionary, when you treat a dictionary like a single collection of key value pairs rather than accessing values by passing it keys, treat it like an array or an unordered array of key value pairs, then whatever you assign to can just be a tuple. So in this case, we are iterating through the scorecard dictionary, which has a type of string keys and int values. In our for loop, we define for the variable for the for loop a tuple, which has basically a constant. It's like a tuple constant with identifier of team and score. And decomposing into a tuple is just this fun thing that Swift can do. But basically, moving forward from here within the scope of code that the for loop defines, you can use the team constant as if it was just a constant, not a part of a tuple. Same thing with score. So because we know the type of scorecard is dictionary of string, keys, and int values, and we decompose into a tuple, it can infer that the type of that tuple is string int. It is a compound type that has a string for the first element, or for the first type, and int for the second. So that means that our team constant here is a string, and our score constant is an int. And when we go to print those things, we see that that's the case. And here's also string interpolation in practice, which is nice. Okay. Sorting methods. So we've talked about arrays, we've talked about sets, we've talked about dictionaries. Let's talk about sorting things. Sorting only matters for arrays. Sets and dictionaries are unordered. You can't sort them. It's not important for them. Arrays, however, ordering can matter a lot. And so sometimes you'll want to sort them, okay? So there are ways to sort in place. An in-place sort is when you modify the variable that the array is. So that is to say, if we have defined a variable for an array called, numbers, right? It's got a bunch of numbers in it. They are out of order when we define it. we can call dot sort. Swift has a lot of predefined sort functions for all of the kind of basic types, like int and double and string and so on. And it can figure out a lot of stuff from like, oh, if you have an array of ints or an array of ints, it can sort that too, right? It knows how to do that. It has its own logic for doing that. However, its logic might not always work for you, but we'll get into that in a moment. So this modifies the variable you're calling it on, the array that you're calling it on, okay? That's the key thing to remember. Now when you call dot sort, you are changing the array that you call that function on. If instead you would like to call a function that returns you a copy of the array that is sorted without modifying the current array that you are calling the function on, you can use dot sorted. Present tense, past tense. Well, I don't know, sort present tense, more like command tense almost, I don't know. But sorted is past tense at minimum. So that's how you kind of know, oh, this is a pretty strong common coding convention, is if a function exists that is in the sort of kind of command present tense and a function exists that's in the past tense, then that past tense function tends to return a copy of whatever you were calling the function on with that operation performed, and the present tense version tends to modify the variable that you're calling the function on. Now let's say that you want to write a custom sort. Let's say you want to sort ascending rather than descending. Sorry, descending rather than ascending. Something like that. Whatever the default is, you want to do the opposite, right? So, in order to do that, we have to use closures, because sort, the function, by the argument label, and then our parameter type is a function type, which we recall from earlier when we were talking about functions and closures. Here, I use, I say type, right? This is to indicate that the type could be, whatever, but the type is equivalent to whatever the elements type of your array is. So if it's an array of ints, then the two parameters going in is int. If the array is of strings, then the two parameters going in is strings. But it always returns a Boolean. And the Boolean is saying true or false if it is, if the left-hand side should be in front of the right-hand side or something like that. The specifics you always have to look up because it's different per language. Cool. Okay, so this is a function that takes a closure. Oop, where's sorted? Hello? Okay, well, there is also a custom past tense sorted as well that seems to have been removed from my slide at some point. So you can do dot sorted by, and then it's the same exact input, the same exact thing. You pass it in a closure, and that closure has, for its parameters, two of the type that the array has, and a return of bool. All right, so let's look at default sorting in place. So here we have a variable called hundreds. It is an array. We assign to it an array, literal, that has a bunch of numbers in it. So these are all ints, 300, 500, 200, 700, 100. This is unordered, okay? If we call hundreds.sort, and then we iterate through hundreds, and we print out each element without adding a new line. Oh, apologies. I wish it would just go back one. All right. Then what this will print is basically 100, 200, 300, 500, 700, no spaces, right? All in one go. It'll look like a big string of gibberish, right? That's because the hundreds variable is getting modified. Of note, you can't call sort on a constant. If hundreds was a constant, if we'd used let instead, you can't call sort on it because that would be changing the constant. You'd be modifying it, which is not allowed. This is important specifically in case you are dealing with a parameter that was passed into a function. So you're inside of the scope of a function, you have a parameter that was passed to you. Let's say it's an int array, right? That is a constant. So if you want to sort it, you have to call .sorted instead of .sort, and then assign the return from that function to a constant or variable that you can then use further on. Here is an example of that with the .sorted function call. Here we're assigning to a sorted constant, and then we are entering the for loop and going through. This prints exactly the same thing, but it's worth noting that we are iterating over sorted, not hundreds. Our sorted constant is a copy of hundreds that has been sorted. Here we have our closure with some of our fun syntactic sugar that we have previously used to make the closure neat and clean and easy to read. Here we have our left-hand side element, our right-hand side element as parameters that are being passed into the closure. We have our in keyword, which says, okay, to the right now we have our code for the closure. To the right and below, we have our code for the closure. Here we have the code for the closure because it is a single statement or expression, or because it's a single expression, we are inferring that it is also the return of the closure. We know that the sort function is expecting for its closure that's passed in for it to have two parameters of the same type as the element of the array and a return of Boolean. So we know that LHS and RHS are ints in this case, and you'd see that with autocomplete in a Playground or Xcode file whenever you're typing LHS after in, right? And then because we are inferring our return, and we know that it needs to be a Boolean, we just say, okay, if the left-hand side is less than the right-hand side, then return true. Otherwise, return false. This is, I believe, the opposite of what is done by default in sort. I believe normally it's like greater than, although I guess technically we're not handling the equals case, so, whoops. But yeah, so here we're kind of the idea is to do a descending sort rather than an ascending sort, all right? Once again, we are modifying the hundreds variable in place. So moving forward from this point, the hundreds variable is now sorted in a descending way. If instead we wanted to create a copy, a sorted copy of the hundreds array, then we do sorted and we assign it to a variable or constant, and then we use that moving forward. Same exact syntax for the closure, though. There are some closure shortcuts. There's further closure shortcuts for sorting specifically. Because sorting is done frequently enough, because there's a lot that is known about sorting, for doing something like sorting in a descending way rather than ascending way, there are some quick little things you can do to further reduce the amount of code you have to write and read to understand it. So to start with, what we had before, because we had a trailing closure for our sort function, was basically exactly the same as this. So we're kind of going in the opposite direction right now just to kind of explain it. Normally we like reduce, reduce, reduce. Here we're going to expand a bit and then reduce. So here, this is the argument label name, by, right? So we're going to sort by this closure. In a closure, sometimes if you know you have like 2 or 3 or 4 parameters coming in, you can use $0 for the first parameter, $1 for the second parameter, $2 for the third parameter, and so on and so forth. I don't personally find this super easy to read. I don't think most people would. Compared to this, this is much more explicit and it's not that much larger. So I would tend to prefer this. However, there are some people who really do enjoy this kind of thing. Basically, these are default parameter names for any parameters passed to any closure, okay? So you don't need the in, you don't need to define the parameter names. You can just say, yeah, my first parameter is 0, my second parameter is 1. You'll find this frequently in things like sort closures that are passed to sort for arrays, just because sorting is very, very well known and understood, and you know that you're always comparing two elements to each other in order to determine where they go in relation to one another. And that has to do with how sort algorithms work. I won't be covering that. Luckily for us, Swift does not use bubble sort. It uses merge sort. So it's O log n time, sort time. So close to the known ideal for sorting. The other thing you can do in Swift with sort is just pass it your operator. It knows that it's comparing two elements. It knows that it's doing it in a way that needs to create a Boolean. So if those two elements have an operator overload defined for them, that is to say, if you have two ints and you can use the less than operator between them, if you have two strings and you can use the less than operator, you can use the greater than operator, you can use the less than or equal to, etc. Then you can just pass it the operator. And it knows, oh, cool, okay. So all I'm doing here is taking this operator and applying it to the two elements that I'm comparing while I do my sort. This is very quick, it's very clean, it's very easy to read, and if you have no idea how we got here, you will be very confused when you read this in someone else's code. So it's one of those things that's really cool, but also it might be better to do this, even though it's a little bit bigger. But it's very cool. As are my animations, but they also slow things down. All right, that's it for strings and collections. We're going to do another 10 minutes here, and then we will talk about language features next, optionals, and error handling. So bathroom break and snack break for anyone who wants it. And I am available for questions if anyone has any.